Hello everybody, welcome back to Calculus. Glad you could join us once again. And we have some good stuff in line for you. Literally lines. Lines that hang between telephone poles. What? He lost his marbles? Well, I lost those long ago, but you'll see. In the meantime, another modern method of proof. Called proof by funding. So if somebody questions your conclusions, just make sure you got the government funding your project behind you. Because then they'll say it's got to be right or they wouldn't give you the money to do it. Okay, our agenda. We got some homework to look at from 3.9, although I doubt if there'll be any questions. There rarely is. Related rates is just an easy topic. And we have to finish 3.11, hyperbolic functions. We just started that a little bit. And since project 1 is getting closer to the deadline, like Monday, seems like you start getting a few questions the class period before. Of course, I know some of you haven't started because it's not Sunday night yet, but suppose you could always email me, right, if you have a question. Then just a reminder that project 1 is due Monday, November 7th. And I have the test 3 review ready. Tentatively, that's scheduled for a week from today. We'll see how things go. And assignment sheet number 4 is also ready. Pardon? What color is assignment sheet number 4? Pink. I think it's pink. Those are also available online, Blackboard. So you can get them there too. That might be nice for the Holland crew, right? You say, yeah, you said that before and it wasn't there. Definitely there. I pretended I was you and I went in there and I could download it. Gotta work. Okay. In case you didn't catch this, there's one thing about the answers that trouble me a little bit, like number 12. It says, find the rate at which the diameter decreases. I thought when you had a decreasing rate, it's supposed to be negative. Well, then why is it listed as positive? Because they ask for a rate of decrease. Decrease is your minus sign. I don't usually do that. I just say, give me the rate of change. And then a minus means decreasing and a plus means increasing. Then you don't wonder, do I put the minus in or do I not? Just ask for the rate of change. They did that again on 18. On part A, instead of asking for the rate of change, they said rate of decrease again, so that took care of your minus sign. And then the next one was rate of increase, which would be positive anyway. Okay, the rest of them were odd, so you could check Bob's answers. But before we do that, so I don't forget, was there anything that came up with your calculator project that you're wondering about? Really? Oh.
Absolute value. I figured that out. Yeah, what was the other one? Is it at the beginning number 3? Keep telling me that you had to say there.
You weren't sure where to find absolute value?
I figured that out, yeah. Oh, where did I go?
Did you?
Yeah.
Yeah, it's go to math and then I believe number. And then it's in the list. We can show you if you like. If you can't find something like that, you can always go to the catalog. Absolute value is going to be right near the beginning because it's ABS.
Yeah, it's math
So,
number.
but it's usually hidden in some menu, and like I say, if you're ever all alone and your iPhone isn't working, just go to the catalog and you'll probably see it in that list. Every function on the calculator is in there somewhere. And they're listed alphabetically, okay? Anything else relative to the project? Yes, sir.
When I had a working calculator, I couldn't figure out how to do cube.
Oh, there is no cube root on the calculator. You just change it parenthesis to the 1/3 power. And the 1/3 should be in parentheses. So they don't really give you cube roots that I could find. They assume anybody who has a calculator like this realizes you can just do to the 1/3 power. They save memory that way, and they can use it for what they consider more important stuff. Okay, so just raise it to the 1/3. Anything else that came up? Yes.
Number 3, will you show me how to type it in? Because every time I do, it says that I'm missing a parenthesis and I'm not.
Oh yeah, famous last words. Missing a parenthesis, and you say, "I know I typed it in."
Well, and they're equal, so I don't know if I need a parenthesis for stuff.
Okay, let me get my project out here a minute. This is problem number 3.
Which defines you. That's what I don't know.
That's on the first page or not?
No, it's not.
Oh, different number 3. Part 2, number 3.
Yes.
Okay. Okay, let's see what we can do. Now, we don't know for sure whether your calculator recognizes secant, and you're sure it does, okay? Okay, we go to F4, we grab define, and we call the function g of x, right? And it's equal to. Now, your calculator only recognizes the square if it's around the whole thing, so you go parenthesis, and then if you trust it, secant of x, otherwise write it in terms of cosine, and then squared. And then it's minus parenthesis, that one's on there though, tangent of x, parenthesis, parenthesis, and then squared. And of course that's the way it prints it out too. It doesn't put the square where it was in the book. And then they wanted the derivative of that. F3 is where all that stuff is according to the instructions. And what do I want to find the derivative of? G of x. And I want to do it with respect to x, right? And the answer, it gives me is 0. And then that's supposed to make you think. Because what kind of a function has a derivative of 0? A constant function. So what's the point here? It must mean that secant squared minus tangent squared is really some constant of some sort. So then you're supposed to think and explain. That's all I'm going to say though. Pardon?
Okay.
No, I'm not going to give the whole problem away. And if you don't know what is happening with secant squared minus tangent squared, you better look at your pink sheet. Might tell you something. Okay, anything else about project? Got one over here. Yes.
Still having that balance problem.
Okay, tell me what you'd like to do.
I'd like to, the last one,
The very last one.
how long does it take the book to hit the surface of the water? I was going to take the graph and find the 0, because 0 is in the water. So I was going to have a 0 on that graph. And I do it below the 0, and I do it above above the zero, and then it says error found.
So he says if you have a graph and you want to use the graph to find the zeros of a function, I remember doing that in pre-calc, but it doesn't seem to work on this calculator, so let us do one.
Well, it does the same thing when I eat it to intersect, so.
Okay, let's see what happens. Let's just do a graph which crosses the x-axis, but not a particular one. Usually if I do a cubic, it's got to cross somewhere. I don't know. It should have at least 1 0, this cubic. Okay? I just went x cubed minus 2x squared plus 3, just to pick something. Then I go F2 6 to see if maybe the zeros show up. And it does seem to cross somewhere, right? Okay, now he wants to find where that 0 is. So he went to F5, which is the math of the graph, and he went to 0, right? And I press enter. And it says give me a lower bound. That means left of that point. It's got to be left. It has nothing to do with up or down, just left.
That's why.
Upper bound means just go to the right of it. I don't care if you're above or below the x-axis, you got to be to the right.
Makes you happier. Alright.
And then it finds it. Now, just one little comment. What kind of answers does it ask for in that problem?
It asks for exact and like decimal.
Okay. It can't promise an exact answer when you use a graph. It'll
Well,
be
I
an
already
approximation.
figured it out using the calculator. I just wanted to check it with it.
Good idea.
And then there was one with the intersect. I couldn't get the intersect. Probably the same reason.
Yeah, lower bound means always left. Upper bound means right.
I got vertically confused.
But that's the same on the TI-84 too. It means the same thing there. But that's okay. Glad we got that straightened out. Anything else relative to the project? Yes.
Part 3, number 4, you have, is with the speed of the book, is that past Rob? It's still a velocity problem.
Of course.
And then,
What's the definition of speed?
distance over time,
Relative to velocity. What is speed?
or direction.
No, absolute value of velocity. Speed is never negative. So the reason speed was asked for is probably because velocity is negative there,
And we're
because
just
it's on the way down. So speed is absolute value of the velocity. Okay?
the specific height that we're solving for? That one, or is just assuming?
Well, it's passing Rob on the way down, so it would be when it reaches the height of the cliff again. See, he threw it up in the air.
Yeah, so we would just be measuring it right where the cliff.
Right when it is at the height of the cliff, yes. We know it's at the height of the cliff at time 0, because that's when he threw it. Then it goes up in the air, kind of does a little parabolic route, and then flies by him again on the way down. Doesn't hit the ground because it missed it, and keeps going down into the water. That make sense?
I think if I had a friend sitting there and I just threw my book and she gives me the stamp equation about how fast my book is going, I'd push off the damn cliff. Obviously, I don't want to hear that.
You'd send her with a book?
Here, go get it back.
I wish I hadn't heard that.
Already pissed at math, so why would I want to hear more?
She deserves to die.
She's just trying to calm you down. get you distracted. What better way to distract a person than introduce some calculus? But it's your own fault for dating a physics major. There, take that. Any other questions about the project? Anything that came up that's kind of bugging you? Okay. Then don't forget, some of you, when Sunday night rolls around, get started on this thing, because it may take longer than you think. It took me about 50 minutes to do the whole project.
Oh, good. That makes me feel better because I did both during lunch today, and I thought, it seems kind of. I have an hour lunch, so I'm like, it seems kind of a short.
Well, I
time for
told
this
you, it
project."
was, the calculator does all the heavy work for you. You just have to think. But some people think more slowly than others, so, you know. Okay, then it's onward to the assignment from 3.9. Is there anything there you'd like to check? Found one you couldn't do?
21.
Which one was it?
21.
21. Oh, I wish I had checked it. You can't do 21. I probably can't either. Okay, number 21, zooming out a bit. Okay, what does 21 say? At noon, a ship A is 100 kilometers west of ship B. It could be. Ship A is sailing south at 35 kilometers per hour, and ship B is sailing north at 25 kilometers per hour. How fast is the distance between the ships changing at 4 o'clock p.m.? That would probably be about 4 hours later, wouldn't it? Okay, I got that part. Okay, what's the first thing we usually recommend we do, if nothing else, to stall for time while we think? Draw a picture, yeah. Okay. I started out with a horizontal line. And on this end is ship A, because it's due west of ship B. And here's B. And how far apart are they? 100 kilometers. Right? Now what's ship A doing? He's going straight south like this, right? And what's B doing? He's going straight north, right? Like that. And wouldn't this represent kind of a arbitrary distance between them? You like that picture, okay. All right. The next step is label the thing. Anything that's changing with a variable, anything that's not changing with a constant. Well, we already put the constant in there. You know, the distance they were apart originally isn't going to change because they're going to do, right, the original distance. So I don't need a variable for that. But how about this distance up here? Is that changing? What do you want to call it? You get to name it. A. So B is traveling A. Okay. What about the distance for ship A here? Okay, and then finally, the distance between them, what I did as kind of a dotted line. Got a letter for that. C. Now remember, C is this total distance, right, on the dotted line. Okay, what's step 2 after you've got it all drawn?
Turn that into a right triangle.
What's step 2 after you make a drawing?
You make an equation.
Make an equation relating A, B, and C together, right? And you say, oh, I'm not sure how to do that. Well, what we used to do in geometry class is make it a little easier by filling that part in. So what is this piece right here? From B down, that's little b. What's this one at the bottom?
100 kilometers.
Okay, now can you make an equation that involves A, B, and C? I'm using this triangle right here. Okay, A plus B, the quantity squared, plus 100 squared has to equal C squared. So in geometry class, we added a few lines so you have a nice one, nice big right triangle you can use Pythagorean theorem on. Remember doing that in geometry? Really? I don't. Wonder why I didn't remember.
Didn't do it.
Because I had geometry 75 years ago. Would you remember after all that time? I should? Oh, he's really kind. What's your name again? We're having a test coming up. I gotta remember that when I grade it. Be kind to those who are kind to you. Is that what it goes? I don't know, never mind. Keep going. Okay, the next step is use symbolic language to describe the problem. So first, what do I want to find? Using your picture. Yes, I want to find dc dt. The rate at which c is changing with respect to time. And when do I want to do this?
4 hours at
Okay, so it's when 4 hours have passed, and as soon as 4 hours have passed, what's the value of A?
140. Oh,
Well, remember A is traveling at
sorry, I got
35?
A is 35.
Yeah, 35 kilometers per hour, so how far will he go in 4 hours?
140.
I actually like the 140, I don't know why you backed off.
I think my name of the variables.
Well, you named him, that's why I let you do it, so you wouldn't get confused with your paper. B would be what? Okay, what would dA dt be, the rate at which A is changing?
35.
And finally, the rate at which B is changing.
25.
Okay, that's everything just taken right out of the reading, right? Guess what else I might want later? C. Because I'm just looking ahead and I'm going to have to fill in something for C. Why didn't they tell it to me? Because you can figure out your own C. Right? Now, I'm not sure what sea these ships are on. It might be the Aegean Sea, the Mediterranean, I don't know. But we can figure it out from Pythagorean theorem what sea it is.
Wait, those speeds are backwards.
Pardon?
Those speeds are backwards.
Oh, sorry.
Ship A is at 35, and ship B is at 25.
Okay. So he says this one's 25. And this one's 35.
Yeah.
Then these will change too, right?
No, those are right.
Oh.
They shouldn't be after 4 hours. They shouldn't be right.
I don't know who would ever choose A and B in this problem when you already got big A and little b, but what can I say? I said right from the beginning, Burger King has nothing on us. We do it your way, but
Change that though too.
what?
If that's the speed of A, the velocity of A, then the distance should be different too.
Yeah, but A is the distance B traveled.
Yeah.
That's why I say
Good job.
this is trying to make a easy problem confusing.
Maybe
that's why he did.
Well,
I mean, I don't know why we couldn't use X and Y that are totally generic, or otherwise little b for B and little a for A, but
why aren't your A's bigger or smaller? You don't have
I'm not gonna argue with you. I don't have time. He labeled it, and I gotta live with it because I can't technically say it's wrong. If it's not wrong, I have to do it. Okay, let's fill it in. What's A plus B? So I have to take 240 squared plus 100 squared, right? And then the square root of that to get C? Are you okay with that? Of course, we would have had that anyway, even if we had messed them up, because it's A plus B. Okay, this would be the square root of what? Does that come out nice? When it comes out nice, then you know you probably did it right, because typically in a math book the problems are rigged so you don't get discouraged. Now in real life this would never happen. But you don't care because you're getting your 50, 60 bucks an hour to do this, and what do you care how the answers look? All pays the same, see? Yes?
You added A and B, right?
I'm just filling this in here.
Yeah, so you added A and B for
Yeah, 140 plus 100 is 240.
that.
Squared plus 100 squared. And took a square root.
Yep.
Okay, next step is go to your equation and do a derivative implicitly with respect to. Here it comes. So there's setting up for my implicit differentiation. Okay, on the left, what do you get? Well, the derivative of a plus b squared, according to the chain rule, is 2 times a plus b to the first times what? The derivative of what's inside, which would be dA dt plus dB dt. Okay, what's the derivative of 100 squared? 0.
What's constant?
Yes. And what about the other side? 2c dc dt. And now we hope we have a number for everything listed except for dc dt, because up here that's what I wanted to find, right? All right, what's a plus b? 340. I mean 240, yeah. What's dA dt? 25. What's dB dt? 35. And that equals 2 times what?
260.
And I do have a number for everything except what I'm looking for. I divided each side by 2 right away. But basically what you have to do is take 240 times, and 25 plus 35 of course is 60, and divide that by 260. And that's dc dt. And if I remember correctly, that comes out about 55.4 kilometers per hour if you divide that. 55.4. Is that sufficient? So what seemed to work the problem? Getting that drawing straight first. And then make an equation, identify what you know, find out what you need but didn't really have written in the problem explicitly. Do your derivative implicitly with respect to t, fill in the numbers, done. Can you do that on the test? Should be able to. I think the only thing a little bit tricky about this one was that drawing, trying to set it up so that there was an obvious relationship. If you use the two little triangles, it's harder to come up with something. As you probably know, right? Okay, on tests I try to avoid something where it takes a little trick to get it going. You know, if you understand the basics, you should be okay.
31.
Which one?
31.
Number 31? Okay, can I safely leave this one? Is everybody okay? In spite of the A's and the B's? You know, even if you mixed them around in the end, it wouldn't matter because you're adding them here and, yeah.
Still kind of confused.
Okay, we're onward to 31. Okay, number 31 says, the top of the ladder slides down a vertical wall at a rate of 0.15 meters per second. At the moment the bottom of the ladder is 3 meters from the wall, it's sliding away from the wall at a rate of 0.2 meters per second. Question, how long is the ladder? That's different. Well, that's kind of why I assigned it. Because usually the question is, at what rate is something changing, right? But this says, how long is the ladder? Of course, the correct answer might be just a little shorter than the former. Might work. Sorry. Okay, step one, what do we do? Okay, so here is wall. And here is ladder. Okay, we need a variable for everything that's changing and a constant if it's not. Is the distance between the base of the ladder and the wall changing? I need a letter.
X.
Is the distance between the top of the ladder and the ground or floor, whatever it is, changing?
Yes.
Is the length of the ladder changing? But I don't know what number to put there, but you definitely want to use something that says I am a... Okay, what do you use if you want to make sure you remember it's a constant?
Ladder.
X.
But the ladder is longer than 0. C is fine. I like K. Because K in just about every math book I've ever had usually stands for some constant. Okay, now I need an equation relating those together. Right, x squared plus y squared equals k squared. Okay, what do I want to find? K. Just want to find k. And under what conditions do I want to find it?
When y equals.
When x is how long? 3 meters? Okay, dx, dt is what?
I thought it was Y, 3 meters.
Well, I don't know. It says when the bottom of the ladder is 3 meters from the wall. But I think we're okay because the
Yeah,
bottom for
yeah.
me is x, right?
Yeah, that makes sense.
Okay, what is dx dt, the rate at which the ladder is sliding? That's the top, that's y.
So we don't have that yet.
Yes, we do. It's written right in my book. I read it.
And the
0.2 meters per second. That's how fast x is changing. And what about dy dt? Okay, that's going decreasing, so it's negative 0.15, and that'd be meters per second, right? Okay, is there something else I might need? Well, possibly, but maybe I'll wait and see after I do it. So I want to now take my derivative of my equation up here implicitly. Okay, what's the derivative of x squared with respect to t? Yeah, power rule, 2x, but then you gotta go what? Chain rule. You're probably into that okay now, right? I mean, you're fine with that? Okay. And then it's 2y dy dt. And here's the part I worry about, because k was a big zero there. Okay, let's see what we can fill in. Oh, look, we could divide by 2 if we wanted to. We don't have to deal with that. Do I have a number for x? 3. Do I have a number for dx dt? Okay, 0.2. Plus, do I have a number for y? Oops. I've got to have something for them, so we'll leave a space. Do I have something for dy dt? Minus 0.15. And that equals 0. Now, when I did that, what's absent? K. There's no k, and I was supposed to find k. Well, that's where the picture comes in. If x squared plus y squared equals k squared, this is kind of off to the side on scratch paper or whatever, then 3 squared plus y squared has to equal k squared, right? Yes? Because it says x is 3. I just don't have any other numbers. But here's the point. What would y squared equal?
K squared minus.
So what is y?
The root of that.
Is the square root of that k minus 3?
Yeah.
You say, that's so mean. You shouldn't even do that to us in Tempest. This is equal to k minus 3 in the Math by Feelings book, so what does that tell you? It's wrong. Everything in there is wrong. Just feels good, right? That book ought to do more to mess up students than any other thing I could have possibly done. That's my final goal as a teacher. What can I do to really mess up students even for the future? Write that book and distribute it to students free. So they can't resist getting it because there's no cost, and then play with their minds. Yeah. Okay, anyway, right here I want square root of k squared minus 9. This was SP, scratch paper, so I could fill that in. Okay, what did I want to find? Oh, k. My equation has k in it now. All right. What's 3 times 0.2? 0.6, very good. I'm going to move everything else to the other side. 0.15 square root of k squared minus 9. You okay? Divide by 0.15. What's 0.6 divided by 0.15? That's how you know this problem is correct, because they're all rigged.
It is.
No, because I moved this to the other side, it became positive. Moved him over there. No. And that equals the square root of k squared minus 9. How do you solve an equation like that? Right, you square both sides. Then what? Add 9. Double rig. So what does that make k? So the final answer? That ladder must have been 5 meters. But do you see, if you just kind of faithfully do your thing, it's fine. It works. Yes.
Could you just found y and just plug it into the...
Yeah, in fact, you kind of beat me to the question. If you didn't want to do this right away, he said you could have just stuck with y here and solved for that instead. And then once you knew what y was, then apply your Pythagorean theorem to get k at the end. Absolutely. That would be just wonderful. Find y first, don't worry about k until the problem is almost done. Yeah. Is that what you did?
Yeah.
That's good. You still got 5, Dan. Okay. So, do you agree? They're not that bad, are they? I mean, just do the routine.
Number 5.
Number 5, the cylindrical tank problem. Okay, we will try. Okay, on number 5, it says we have a cylindrical tank with a radius of 5 meters. It's being filled with water at a rate of 3 cubic meters per second. How fast is the height of the water increasing? They didn't say when. Why not?
I don't know.
Well, if you draw a picture of a cylinder, which looks something like that, what can you say about the rate at which the height is changing? You know, you're going to pour water in there at a constant rate. So what can you say about the rate of change in the height?
We constant.
It's constant too. It's the same at no matter what time, what point. You see, if this were a cone, then the height would be changing at a different rate. But since it's a cylinder, the rate of change in the height is just constant. It doesn't matter where you do it. Okay. Is the radius of this cylinder changing?
No.
So then I want to represent it by a constant.
5.
Okay, is the height changing of the water, if this is the water? Is the height of the water changing? What do you want to call it? Okay, now I got to make an equation relating the stuff in the picture. And that just comes, as often is the case, from a geometric formula. Do you know volume of a cylinder?
Pi r squared times x.
But for mine, since the radius does not change, it'd be,
5x. 5x.
right? Okay, what do I want to find? dx dt according to your labeling, and when do I want to do it?
When, not sure.
Remember what?
Well,
PDT equals 3.
yep. And that, of course, is 3, what was it, meters cubed per minute? But am I going to have to fill in something for x? I don't know. I'll worry about that later. Okay, now it's time to go for the finish. Using the one I starred right here, the derivative of v with respect to t has to equal the derivative with respect to t of 25 pi x. Okay, the left side just becomes dv dt. That's fine because that's what I'm looking for. The right side becomes the derivative of this, which is 25 pi, times the derivative of x, which is dx over dt. So you see how it all kind of takes care of itself?
And that's just because x would be 1.
Well, the derivative of something times x is just the coefficient, right? And the reason that worked out is because x, the rate of change in x, is going to be the same everywhere. Okay, what do I put in for dv dt? 3. Okay, do I have a number for everything except what I'm looking for? Actually, yes, because I want to find dx dt. And so I would say the answer is probably 3 divided by 25 pi. And that would be meters per minute. That's how fast it's changing. 3 divided by 25 pi. Is that okay? And the reason it worked out that way is it doesn't matter what the value of x is. The rate of change is going to always be the same. And the math knew that because when you took the derivative of this side, there was no x left. Not like there was an x squared there, then it'd be 2 times 25 pi times x to the first.
So
But
if you're taking the derivative of just x, it's just dx dt. Right?
well, come on, what's the derivative with respect to x of 5x? Do you stumble on that?
5.
Oh, just 5, right? What's the derivative with respect to x of 5 sine x?
And be 5 cosine.
5 times the derivative of sine x. And that's why if I'm doing the derivative with respect to t of 25 pi x, it's equal to the coefficient times the derivative of x. And since I'm doing it with respect to t, it doesn't go away. Get that? All very consistent, even though it looks weird.
So excess should be banned from this lecture.
Okay, anything else from related rates?
Number 27.
Yeah.
On the test, are there going to be questions that require formulas and stuff? Like,
Oh, good question. Yeah, I said on the test eventually with a related rate problem, am I going to have to recall some formula that I did back in the 6th grade? Maybe. But the upside is I'm not testing to see if you can remember formulas from the 6th grade.
Give them the backup.
So what I typically do, if it demands some geometric formula, I have a little parenthesis with a problem saying, by the way, I don't mean to insult you, but the area of a rectangle is base times height.
Great.
Now, I may assume that that one's so obvious that it would be insulting to put it in. Then what if you didn't remember?
not that I was asking.
You just
about the
ask.
area of a rectangle, but I mean, like,
Yeah, I
if
know.
I had to write the area of a rectangle on my pink sheet, would that be a deal?
No, don't write it on there because, like I say, it'll either be printed on the test, or if it's not there and you need it, you just ask me and I'll tell you, because that's not what I'm testing. I'm testing to see if you can do calculus.
So we're not gonna have to know about the area of a rectangle.
For algebra questions, right?
That's all I'm asking.
That's all fine.
Because if we're talking about the area of rectangles, might want the pink sheet.
Of a rectangle? How about it?
Yeah.
How about surface area of a
Calculus
cone?
class, man, I don't have to answer these questions.
What
I'm
about
here for calculus.
what about surface area of a cone? Now there might be one that not too many people remember, right?
Yeah, I was kidding.
So I would give that to you. And if I forgot, you just ask and then I'll tell you. In fact, I'll tell the whole class. But the person who asked about what's the area of a rectangle, their name goes on a bulletin board in the math department saying such and such is taking calculus and doesn't know how to find the area of a rectangle.
You all
It's,
passed me.
it's no big deal.
That is actually an accomplishment.
It's no big deal or anything.
Got it this
Just,
far without
just a minor little blip in the screen, okay?
Get through math without knowing the area.
Look them up and stuff.
Think. Okay, any other questions? But that was a good question, because I'd worry about the same thing. What if I don't remember the formula? Like, I just wrote down volume of a cylinder, right? Pi r squared h. And you say, what if I didn't happen to recall that? Don't worry about it. It'll probably be printed by the problem, or if it's not, just ask. Okay, Kelly.
You do 27, please.
Okay, take a look at 27. Where gravel is being dumped from a conveyor belt, right? All right. For those of you at home that were too cheap to buy the book, now you're going to wish you had bought it, because there is a picture before your very eyes of a conveyor belt dumping gravel. All that comes with the book at no extra charge. And they're saying when you dump that, it naturally makes a pile that looks like a cone. You know, that's true too. Well, it's always kind of nice when what they say actually is realistic. You know what the latest buzzword is for realistic problems? Authentic. Authentic. You see, for quite a few years it was, we have to do real life problems or the students will get turned off. And then after a while, when students got turned off on real life problems, they said, we got to make them authentic. So that's the latest buzzword to get you turned on. Same problems we always did, just new word. But I'm not supposed to tell you that. You're supposed to figure that out for yourself. Okay, back to the problem. The picture, of course, is that cone, that conical shaped pile. So we will kind of replicate that. And there's my cone. Okay, the question is, what's changing? Does the radius of the base change as you pile more gravel on? Ah, so I need a letter for the radius.
Oh, I thought it was
Did
the
you
di-
pick one, Kelly?
Diameter and the height are supposed to.
Pardon?
Says they are equal.
I know.
Okay, then it'd be,
But I'm talking about volume of a cone, and usually they write it in terms of the radius.
Which one is this? This is
So could I have a letter for the radius? You can give me one for the diameter, I don't really care. Pardon? For the diameter or the radius? Okay? Okay. Which says to me she wants it to be constant, but okay. Play games with me. What about the height?
how about,
Kelly?
H.
H. Okay. Now I've got to write volume of that cone. Now you may or may not remember, but if you don't, it's not an issue. For now, it's in your book. Think in the front cover or something. But that's what I kind of recall. 1/3 pi r squared h for volume of a cone. Okay? All right, now let's write what we know. What do they want me to find? So dh dt. No, they don't want me to find h. They want me to find the rate at which it's changing. And I want to do that under what precise conditions?
When H equals.
Okay, when h is 10 feet. Okay, that's good. What else? Okay, when h is always equal to k, which implies something, doesn't it? So I want to do it not when h equals k, when h equals 2k. There we go. Because the height is not equal to the radius, if I read it correctly, it's the same as the diameter. So it's 2k, which is the diameter. But what does that imply? So when h is 10, what's k? 5. Yeah, that's all I needed. Right? Okay, is there anything else they gave me? Actually, they did. What else did they give me? I got to put it in my symbolic notation. Come on, when they say rate of 30 cubic feet per minute, they're giving you what kind of a measure?
volume?
Volume. So it's dV dt. The volume is 30 cubic feet per minute. There, now I got everything. Okay, I'm going to go to that equation at the top of the page, and I'm going to do the derivative with respect to t, just to do something different for once. I'm being sarcastic. Teachers aren't allowed to be sarcastic. They're supposed to always be straight arrow and nice. But then you won't get prepared for life. But you're on national TV and they all witnessed you being sarcastic. It's okay, fire me if you dare. Get somebody else to teach this class on national TV.
Plus, I feel like we're kind of thrown into something between you and the administration, which is okay.
What does that mean? Oh, I was supposed to use K here, sorry. I get along fine with the administration. I just wonder if they ever watch this class. That's my way of finding out. Should be 1/3 pi k squared, right? Because we use k for r. All right, what do I get on the left? The derivative of v with respect to t?
It's 30.
Well, not yet. That's later after I do my derivative. Okay, I've got to do this part. What's the derivative of 1/3 pi k squared? Well, I'm going to view this as something else to make it a little easier. Because how are k and h always related? That'll make it a little easier to do the derivative. Then I won't have to use product rule, although that would work. It's right here. So can I not write it as 1/3 pi k squared times 2k? See, that way I only have to work with one variable, and then I don't need product rule. So I'm now down to the point that dv dt is the derivative with respect to t of 2/3 pi k cubed. Is that okay? Just simplifying that. So what is dv dt before I fill in my numbers? What's the derivative of 2/3 pi k cubed? K as a variable. Power rule, 3 times 2/3 is 2 pi k to the second times right? Okay, what do I put in for dv dt finally? 30. That equals 2 pi. What do I put in for k squared?
25.
Okay, 25. And that's dk dt, right? So what do I end up with? 30 divided by 50 pi. And if I reduce that, okay, why did that turn out to be the final answer for the other one too?
Which one?
Because they asked for dh dt.
As for dh, dt.
Yeah, they wanted the rate at which the height is changing.
They're changing at the same.
Because they're changing at the same rate because they're related in a linear fashion. Does that make sense? So the rate of change is the same because one is just double the other, and the rate of change is going to be the same.
Wouldn't it be times that?
No. And if you're inclined to do that, then back here I should have written the whole thing in terms of h so you don't wonder. Then you know for sure. But I know that if there's a linear relationship, the rate of change is the same.
I think you did something funny there.
I know.
All right.
I'm waiting for you. I keep fishing around waiting.
I don't know what it is, but
Yes, you do.
something's not right. Well, I know that's not
I
right.
divided by 5, and I got 5 here, and it should have been,
Well, it should have been 10, but
yes.
the answer really is 6 over 5 pi.
Yeah, but now if you reduce again, you're going to get 3 over 5 pi.
Oh, I know what it is. Yeah. I don't like that one.
And now h is twice that, and that's where you get the 6 over 5 pi. So I was pulling your leg. You're correct. If you get k, h is twice as much. Probably the safest thing to do here is, when I went back here and wrote it strictly in terms of k, I should have written it strictly in terms of h.
Wait, what happened? I
I
didn't
don't
see
quite
what you
understand
did.
how H is
Got
or the other way around. It said that H and K were always equal.
No, it didn't. One was twice the other. K is the radius. It says height and diameter were equal.
But does it matter the value if it's rate and always remaining equal?
No, one is changing twice as fast as, because we're comparing to the radius.
Oh, and one has to change twice.
The height
as
is
fast.
changing exactly the same as the diameter, but the radius is half the diameter.
Okay, well, you
So
had-
it's changing twice as fast as the radius. You were right. Is that okay?
You had me convinced. You
Oh, I was just playing with you, but I shouldn't do that.
What's the answer? I still don't get over it.
Well, I guess I learned my lesson.
Yeah, don't pull that.
Don't assume that your intuition is going to help, so I'm going to just work it in terms of h, and then there's nothing more to be said. Because obviously I can't convince you any other way. So instead of writing all in terms of k here, I'm going to write it in terms of h. H is equal to twice k, right? This thing is k cubed or 2k cubed. So I want to write that in terms of h. K is equal to h over 2, isn't it? Okay, so this would be 2 times h over 2 cubed. And then we'll go directly to h, which is what we're looking for. Okay, you can see that I have 2/3 pi just like before, but h over 2 cubed is h cubed over 8. Is that okay? And I can cancel one more time, and so I end up with d dt of what? 1/12 h cubed, and that's what dv dt is in terms of h instead of k, because h is what they wanted. Okay, now we'll do the derivative on the right. If you multiply by 3, you get 1/4 h squared, and that's times
3.
dh dt. 3 times 1/12, h to 1 lower power times the derivative of h. Okay, over here we put in what? 30. Nobody argued with that. What do you put in for h? Well, near the top of the page, here it is. H was 10. This would be 100. dh dt. I lost my pi though. pi in there. 1/4 of 100 is how much? So 30 is equal to 25 pi dh dt. So what does that make dh dt, which is what I wanted in the first place? Okay, reduce it by dividing by 5. And there it is, the answer. Working it out with a variable in there that you're looking for. So what if you did work it in terms of k? Just like your intuition said, k is only increasing at half as much as h is, so you got to double that answer. That is exactly right. Because they're not exactly equal. One is half the other. Is that okay? Do you believe it now that that's the right answer? Well, it is an odd problem, so you could look it up in the back. Then you'll know for sure. Any other questions on related rates? Oh, there's still some left? Okay, 39 will be our last one, and then that's for today. And then I want you, if you aren't doing as satisfactorily as you'd like, then try them again, the ones we didn't do, and see if you can make them happen. If they don't, bring it up Monday. And I'll gladly go back to this section and look again. It just doesn't happen. Now, I believe in the test review, there's 3 more to practice on. That kind of shows you the caliber of the type you have to do on the test eventually. So, if you get a chance, I would check those 3 off the test review over the weekend too, just to see if you're going to be okay with related rates. So you have a chance to bring it up Monday again and say one more time. Well, the project, most people have it done because you had 2 weeks to do it.
But it's due on Monday.
The project is due Monday, yeah. Okay, you said 39? Okay. Okay, on problem 39, we have this television camera. It's 4,000 feet from the base of a rocket launching pad. Did you want part A or part B?
Just
A, and after we do that, then you should be able to maybe do B. B involves an angle, so that would just be a trig relationship. Just pick one that works. Okay, first of all, the picture. Right here, I'm going to call this point C, that's where the camera is. And it's 4,000 feet from the base of the launching pad, LP. Okay, we assume that the rocket is going up, right? And question A says, how fast is the distance from the camera to the rocket changing? That would be that side. Okay, you notice we put 4,000 in right away because the distance between the camera and the base should not change. If it does, it's time to get nervous. Okay, is the height of the rocket changing? He's going up this way. You have a letter for me? H. Okay, is the distance between the camera and the rocket up here changing? Yeah, it's getting longer and longer, isn't it? You have a letter for that. D? Okay. Now give me an equation that relates D and H together for part A.
squared equals squared plus 4,000.
Very good. Okay. Now I want to write exactly what I'm looking for. what are they asking me to find in symbolic language?
The derivative of,
So I want to find d dt, right? That would be symbolic language for the rate at which d is changing. And when do I want to do it?
that's the part I don't really know.
Okay, notice it says, assume the rocket rises vertically, its speed is 600 feet per second when it has risen to a height of 300 or 3,000. So h is 3,000 feet, right? And dh dt, which represents the speed of the rocket, is how much at that time? Okay? All right, now we'll go back to this equation that I underlined several times and do a derivative with respect to t of each side. Okay, what's the derivative of d squared with respect to t? 2d dd dt. Other side, what's the derivative of h squared? 2h times. And what's the derivative of a constant, no matter what it is? Okay, now let's fill in our numbers. And right away, well, we can cancel the 2's, right? Divide each side by 2. That's up to you. But right away, I encounter a d. And I look back at my list here, and I had no d. So I said to myself, it must be I could find that on my own. So you go back to d squared equals h squared plus 4,000 squared. And you put in your 3,000 for h. And then they're kind of hoping you recognize the 3, 4, 5 right triangle. Remember those days? Pythagorean triples, 3, 4, 5, 6, 8, 10, 5, 12, 13.
5,000?
So D is going to be 5,000, but feel free to work it out. But I put 5,000 here. And what do you put in for H? 3,000.
Oh, there it is. Six.
And the DHDT? 600. Okay, just divide each side by 5,000. And you'll get that 360 that we gave you for an answer, that Bob gave you for an answer. That's sufficient? You can do that, right? Now for part B, it's the same picture, but they want to know how fast this angle is changing. So you just have to make an equation that has theta in it. If you use tangent of theta, it'd be h over 4,000. If you use sine of theta, it'd be h over d. If you use cosine of theta, it'd be 4,000 over d. They all work. For me, the fastest one was tangent because it used h and 4,000, and those were furnished originally. On the other hand, if you did part A, you already know D is 5,000, so it's like you know what it is when you fill it in anyway, so it's not an issue. So see if you can make it happen. Rounding it off, it's about 0.096 radians per second is how fast it's opening. If you want to know what that is in degrees, multiply 180 and divide by pi. But they always give their answers in radians, so. Okay, that is the last one we'll be doing for today, but I do invite you to bring up anything you encounter over the weekend if you practice some more and try the ones that you didn't get. But we pretty much have done the ones that are controversial at all. Others are fairly straightforward, but if it doesn't happen, let me know. We'll kind of rip it apart. Okay, I think it's time for a little break. And when we come back, it's hyperbolic functions, trying to see how they act and what they're good for. So we see you back in about 10.
I have one last question. When you say, write complete explanation, when I write the definition, is that a complete explanation, or do you want complete sentences?
No, no, no. It's typical math. It's not an English paper. It's just explanations or you could say words and say, I use this.
I use this equation to,
That's all I want. I just want to know what you were thinking.
okay,
And if you just give me an answer, then I don't know how you did it.
okay. Well, this is what I was thinking. Do you think that I should write more?
No,
For
I
this
can
one?
see what you're doing.
Okay, wonderful.
Yeah. I'm not sure why you did it that way, but it's fine.
Oh, really? Do you have any suggestions?
No, no, it's not going to give you a better answer.
Or was there an easy way to do it?
Well, what was the question on that one?
That's one more page over. Oh, wait, no, sorry, one page back.
I thought it was here. No? One back further from here.
Yeah.
There it is. Right here?
Mm-hmm.
What was the average velocity of the book? What time it left his hands? Time it hit the water? Well, average velocity is the slope of the secant.
Can you find that by,
Change in distance divided by change.
Hmm?
Is that what you did?
I could do that. Sure. I thought you wanted us to use a limit.
No, whenever it's average velocity, it's not a calculus problem.
Okay,
Because it's slope of the secant line, which is given 2 points, find the slope.
okay, that's easy, but, okay, I thought that,
If you do a limit, then you're getting instantaneous velocity. Instant. So if it's average velocity, you just want to find what was its height at beginning and end. Divide that by how much time it took.
okay,
That's it.
That's
It's an
easy.
arithmetic problem,
I
basically.
could do that one.
Provided you know those values, of course.
Mm-hmm. Yeah, I figured them out already.
Okay.
How would I know if, so, could I get this general formula directly?
Well, how would you type it in? How do you do a derivative? You type it in the calculator.
Did the D,
Then the function, right?
mm-hmm,
F of x. Whatever we called it. Derivative of your function f of x, whatever it is, comma. Comma what?
this one would be N?
Well,
Haha,
there you go. No. No. N is at the end. Remember, it's first x and then it's which derivative you want.
oh, yeah, okay,
So if it's a sixth derivative, you put a sixth here. If it's the nth derivative, you put an n there. So you type that in and see what it comes. Either it gives you something or it doesn't.
okay, thank you.
And I just want to know if you followed the pattern and said, well, if I want to do an nth derivative, I put in there.
Okay,
Does the calculator understand?
that means,
Yeah.
thank you very much.
I was really questioning myself when I went through this, doing it, it's like, this is too easy. calculator, when I put it in there, it gives me ln of e instead of 1 for,
Because you use the letter E instead of the number E.
right?
Probably. Yeah, if you get it off the keyboard, it's the letter. You gotta go to the math section of your calculator to get E, which is second ln. Then it's the number E. Of course, on this calculator, whenever you go for the number E, it says put a power on it. But that's not an issue, put a 1 up there. They give you 1 now?
It gave me 2 times then the derivative. And then someday. If it's 4 and they're twice, I'm assuming it's supposed to continue to 5.
Yeah, if you gave me 4 back again, I can't say anything because that's what it says. I didn't catch it until I had him run off. So if you read it literally, I'll accept it. But yeah, I did really want 5. No point in doing 4th derivative twice. Spell check didn't catch that.
I think that should be on a test, have the same question twice.
That'd be fine unless somebody didn't know how to do it the first time.
Yeah.
You put n in there, they give you domain error. So that same problem, in the calculator, get this general in terms of n.
It just didn't really give. It just didn't come up with the form that made.
How'd you type it in? How'd you type it in?
I did the derivative of it, and then instead of putting a number at the end, I put n,
Did you
and it says domain error.
comma X and then comma N?
Yep, comma x, comma n, close parentheses.
Well, I guess some calculators do that. The point is still the same.
Was it supposed to give you that, except instead of the number, it gives you just n?
Yeah, it doesn't always include this at the end, it just gives it right back again,
Okay,
which means it can do it.
okay. So do you want me to put the domain error, or just?
No, just,
throw it in there,
the
yeah?
question was yes or no, right? Can the calculator do this directly? And for 1 point, answer is yes or no. Mine couldn't do it either. Somebody did, thank you, I'll hand them all back.
Oh, okay, cool, I thought.
That's what I was gonna do while I was waiting. Thank you.
Problem.
I'll remember.
There, no, what I did.
Yep.
These are very answered.
You guys skipped Monday because it was Halloween?
I was sick. I wasn't sick. I was hanging out for
So how did related rates go?
Oh, I planned on watching the video. Not yet now, but I did look over it.
Now you don't have to, because over all those problems.
Not gonna be on the test?
Of course.
What I say, everything. Keep making rounds.
I got more people shirts than you.
But you get
Oh,
missed.
yeah, sure is nice. Was up there for a couple days.
Yeah. I mean, they've got horrible shares, but they could be a lot better.
Or material. Not bad.
Quite know what this port does. I couldn't tell you. They didn't give me a key. It's like this says I have a wish. It's not me. It's I had a cable.
Okay, we are back, and we are going to continue with 311, the hyperbolic functions. And just a brief review of where we left off. This is section 3.11. The last section that will be covered on the test next week. We've been working on the introduction. We have a little more to do. And the first thing we did is gave you the names. And that's why I mentioned when I studied these, they were called hyperbolic trig functions because the trig seems to play a big role. Sinh, cosh, tanh, and all that fun stuff. Then I was looking at the origin of names, and the hyperbolic part came from the fact that graphs of hyperbolic functions tend to have what?
Parabolic.
Asymptotes. And out of all the conic sections, circle, ellipse, parabola, hyperbola is the only one that had asymptotes like that. So it has asymptotic behavior similar to what a hyperbola has. Now we did do an example of y equals cosh of x. And it looked a lot like a parabola, but we superimposed the closest parabola we could find on top of it and found they were not following the same path. The question I did not answer was this one. If this is not a parabola, what is that thing? It's not a hyperbola either. The official name for the graph of y equals cosh is catenary. It's called a catenary curve. And I invite you to look up maybe and see where that name came from, although you'll probably figure it out. Okay. The other one, and this is where we start today, is the trig part of the name. Where does that come from? And the answer is the properties of these functions are similar to those of trig functions. Now I had a little bit of a dilemma at this point because there's a huge list of properties and they are in the book and they go on and on. But then I thought, well, what could I do to make it worthwhile for your showing up today? And so what I took time to do between Monday and now was I worked every problem in 2.11, just for entertainment, sort of. Recreation, 211. 311, I mean. And then I checked when I was finished to see which properties do I need really to work these problems. And then I narrowed down the list, and I will tell you which ones you need to survive. Now, there are more if you want to look them up, but these are the ones that are necessary to survive. Okay, the next question is, will I ever be able to remember these? Well, some are really obvious because if you know trig, you're going to know these. But when there's a little quirk to them where it's almost like the trig, but one slight difference, that's where it's easy to stumble. But to make a long story short, you may write as many of these properties as you think you want to, provided you still have room. I told you not to write very big on there, on the back of your pink sheet. So you can do that later, whatever you want to do, okay? You can kind of decide. And the pink sheet, of course, is valid for tests to have out. So you can kind of decide. Okay, you remember trig had Pythagorean identities like sine squared plus cosine squared is 1. 1 plus tangent squared equals secant squared, stuff like that. Well, hyperbolic functions have kind of Pythagorean identities too. But before we do that, are they related to each other? Well, do you remember tangent of x? It's related to what? How is it related? Sine x over cosine x? What about secant? 1 over cosine, remember that's basic trig. Most people know those because they just sort of remember it. Okay, here's some for the hyperbolics.
We can write these on the back of our pink sheet.
Yeah, whatever you think you might not remember, but I think some of these you won't need. But number 1, if you take hyperbolic tangent of x, guess what it will still be equal to? Now you don't know why it is, but you'll find that out shortly. But it's still sinh of x divided by cosh of x. Same as what the trig is.
Are they all like that?
No. That's the tricky part. Just about the time you get overconfident, you say, oops, something's different. Okay, but if you take hyperbolic cotangent, coth of x, yep, it's still cosh of x over sinh of x. Same thing. Likewise, sech of x, yep, still 1 over coth of x. You say, well, I don't need to write anything. I remember these from trig. What about the rest of them? Well, we could write them in here, except you won't need them, so I didn't bother. Okay, number 2. Remember sine squared plus cosine squared is 1? There's something like it, but this is what it takes. It's cosh squared of x plus sinh. No, it's minus. So just about the time you get a little overconfident, and most of the differences are a slight sign change somewhere, like where it used to be plus, it's minus. And of course, if it's minus, it matters what you write first and second, right? So that's a Pythagorean identity. It's sort of like trig, isn't it? It's just that it's minus instead of plus. Well, do you remember 1 plus tangent squared was secant squared? Now it's 1 minus hyperbolic tangent is equal to hyperbolic secant. So instead of 1 plus, it's 1 minus. So in the Pythagorean identities, there's just a slight little change. And that's what'll get you if you're not careful. Okay, some more that you might need in the assignment. There's sinh of 2x. You remember what sine of 2x was on your pink sheet? Or do you remember it in your head? Usually somebody does. 2 sine x times cosine x. Well, guess what? This is still 2 sinh x times cosh x. So we're right back on target again. It's identical to the trig. Now, if I were sitting where you are, I would say, well, where's he getting this stuff from? Hang in there. You'll see. We can verify every one of these. Okay, another one that'll come in handy is sinh of opposite x. Do you remember what sine of opposite x is? Is that one on the pink sheet? I don't remember. Sine of minus x, is that on there? Oh, okay, it's minus sinh x, same thing. What if you take cosh of a minus x? I don't know, what was cosine of minus x? Pardon? Oh, well, this is still cosh x. So number 1, matched the trig perfectly. Number 2, messed up the signs on you. Number 3 and 4 matches the trig perfectly again. Okay, there's one more which are essential to work problems. And that is, what about the sinh of an x plus y? Well, I don't know, is sine of x plus y on there? No, but sine of u plus v is, and you can adjust the letters, right? You remember how sine of u plus v went?
Sine U,
Okay, so this is sinh x cosh y. And just like the trig, it's plus cosh x sinh y. Matches the trig perfectly. Okay, the last one, in order to survive in the homework, is the cosh of x plus y. What about cosine of x plus y in the pink sheet? How did that turn out? Can you find it?
cosine,
Cos- Cosine x,
cosine.
cosine y, then what? Minus, yeah. Minus sine x sine y. Yeah, it's a little tricky on the pink sheet. You gotta look, whether the plus is on top or the minus is on top.
They flip.
Yeah, you saw that, didn't you, on the pink sheet, how to read that? Well, this one is just like the trig, cosh x, cosh y. But right here, about the time you get confident again, instead of minus, this one is still plus. But then it's still sinh x times sinh y. Okay, we could make this list 4 times as long, but these are the ones I sorted out that are essential to doing your homework. And if you need more properties, they're in the book, but these are the basics that you need. I just summarized those. So, what are identical? The first one, the third, and the fourth are identical to the trig versions. 2 and 5, slight changes on cosh at the bottom. Okay? All right. A little note that I insert here. Since all hyperbolic functions can be written in terms, just like the trig, of sinh x and cosh x, we deal primarily with those two. Okay? So most of our focus will be on sinh and cosh. Because if I do have something like coth, I can always write it as cosh over sinh and then go from there if I need to, if it doesn't work directly. Okay, the next point is, what are these functions? What are their definitions? You see, when you took trig, we defined each of those functions, and we looked at that unit circle, remember? It's even on your pink sheet. And what was sine of x defined to be, or sine of theta? Well, you draw that unit circle, right? And then you look where the terminal side of the angle intersects the circle, and then cosine is the first coordinate of that point of intersection, and sine is the second, and then from there you can get the rest. Well, it's only fair to tell you, well, where did these come from? It's okay to name them and tell you how they act, but my question would still be, where did they come from? What is sinh, really? Is it the second coordinate at some point, or what is it? Well, actually, these are almost easier to define than the trig, because this is where they come from. So this is finally B, definitions of the hyperbolic functions. What are they? What can I relate them to? Number 1, what really is sinh of x? You can get sinh of x by taking e to the x subtracting e to the minus x and dividing by 2. No, that may not be on your pink sheet. You have to know that one. So sinh can be defined, surprisingly, in terms of what? The exponential function. Well, what about cosh? It's very similar. It just happens to be e to the x plus e to the minus x over 2. Well then, what is tanh? Well now, if you have the first two, couldn't you figure out all the rest? Because if you do sinh over cosh, what's going to happen? Can you just look at it and see it in your head?
Is it gonna be,
The 2's will cancel because when you divide, you multiply by the reciprocal. Well, once you have tanh, I guess coth is easy. Because coth and tanh are what?
so you can just memorize the first two and you can find
That's
the
the point we're trying to make, yes.
other. Okay, sorry.
No, that's fine. I'm glad you pointed it out. That's what I was hoping would happen. Well then, what about sech? Well, that's reciprocal of cosh, so that would just be
Over EX minus,
And what about chech? Chech of x. 2 over e to the x minus e to the minus x. And there on one screen are the definitions of the 6 hyperbolic functions. They all can be written in terms of e. Okay. The next step along the way is to look at the asymptotic behavior of the graphs. So that's C. Now that I've got them defined, we can actually explore that further. Asymptotic behavior of graphs. Okay, we're just going to look at a couple of these. But first of all, I have to do my Toyota trick and ask if you can recall what this graph looks like. E to the x divided by 2. Also known as 1/2 e to the x. So what would it be? Well, normally e to the x goes through what famous point?
1, so
0, 1. So where would this one go?
0, 1/2.
Right through there? Other than that, because remember it just shrinks the distance from the, wouldn't it be one like this? Well, what about y equals e to the minus x, the other component of cosh and sinh? Well, you know what e to the minus x did earlier, didn't you? Kind of decreased instead of increased. So again, it'll go through that point 0, 1/2, but it'll come down like that and approach the x-axis as an asymptote. Okay. The other one I need, though, to accommodate everything is the opposite of e to the minus x over 2, because sometimes there's a minus sign in front of it. But I think once we've done this one, do you remember what a minus in front does? Flips it over or reflects it over the x-axis, so that would be one like this. Okay, we may have to pull those graphs back momentarily. Okay, now that we've recalled what e to the x graphs look like, now what about y equals cosh of x. We already did it on the calculator, and it looked a lot like a parabola, but it wasn't, and it was called a catenary. Okay?
Go up just a tiny bit. I meant down, my bad. I can see the last graph. Go up a little bit more if you want.
Here's the 3. This is e to the x over 2. This is e to the minus x over 2.
Add each half? Get that?
Pardon? Okay, now back to here. Doing this would be the same as doing this one, right? If my definition is right. But cannot this one be split into e to the x over 2 plus e to the minus x over 2? Okay, if I take the graph of e to the x over 2, this first one, and kind of put it on here, it'll come like this. It'll curve around like this, and guess what? Yeah, it's not a straight line, but it's a curved asymptote that this will follow. And this one is y equals e to the x over 2. What about the other branch? Well, that's going to follow this one on the left, and that's y equals e to the minus x over 2. So what's the point here? Y equals e to the x over 2 is an asymptote on the right. Y equals e to the minus x over 2 is an asymptote on the left. And since we got those fancy calculators, let's watch it happen. And that way, if you need to doze off for a minute, you get your chance to do so. And we'll wake you up after the calculator demo is done. Are you ready? I want you to kind of see this happen. Okay, I'm getting some yawns. That's a good sign. Okay, the worst part is having to zoom in on this thing, but eventually it happens. Okay, going to the graphing screen, deleting what's there. The first thing I want to graph is cosh. Do you remember how to find it? Okay, second 5. Go to where? Hyperbolic, you can just type in C if you want to. And I want to do cosh again. And I have to put the argument in. Okay, that'll give me that same graph we viewed on Monday. Now, the next one I want to do for y2 is the first asymptote, which is supposed to be e to the x divided by 2. Okay, like that. Make sure you use the number e, not the letter e. The next one is e to the minus x divided by 2. Okay? Now my claim is you ought to see asymptotic behavior between those second and third curves. Okay, the window that worked really nice for cosine, you may or may not remember, was go from, yeah, it was minus 4 to 4 in the x. And for the y, we suggested minus 1 to 15. Okay? And now we're going to graph it in that window. The first thing you will see is the actual graph of hyperbolic cosine. Looking like a parabola, but really being a catenary. The next graph you will see is 1/2 e to the x. Notice it comes, and it gets so close so quickly that the resolution isn't enough to even see the difference. And then eventually the other one comes down. Now, how can I verify it's really an asymptote, they don't become one and the same? Well, you could go to zoom box and then go up here somewhere to where it looks like they're the same curve. And we'll get really close. Make that one, and then we'll go down. Then across. Right there. And we'll make that box be the entire screen. Very small box, but it goes through it, right? And if there's really an asymptote there, what should I see?
Little.
Two separate curves if I zoom in far enough, okay? Here comes the cosh. And here comes 1/2 e to the x. You can see barely there are two curves there. I guess if you really wanted to separate them, you got to zoom in again.
Graphic.
We'll make that one corner. And across something like that. Here comes the graph of cosh, and here comes the graph of 1/2 e to the x. Do you believe me that there's asymptotic behavior there? There are two curves, and I had to zoom in twice to really get them to be separate, but they always will be. And if you zoom in far enough, and you can see my window here, there's not much separation there, right? It's 3.1407, and it's 3.1456. Not much separation to see the two different curves. Okay, and we could do the same for the other. Okay, zooming back out. Isn't it nice I do that once in a while? That gives you a chance to just ignore me totally and talk to your neighbor instead. That's part of the reason I do it. Okay, the next one is y equals sinh of x. Okay, this time I want you to remember it's e to the x minus e to the minus x over 2. So guess what my two asymptotes ought to be? And then we'll graph all three at once again, because we haven't seen really what sinh looks like. Guess what one asymptote is, based upon the previous one? Not quite just e to the x. Yeah, it's e to the x over 2. And guess what the other one's going to be? Yeah, just think of separating the fraction like we did before. So this is one of them, and this is the other, so it's minus e to the minus x over 2. Okay, using the same logic we used before, just break up the fraction and use the two pieces. Okay, now we will watch that one happen. Okay, this time, instead of cosh, I want sinh. So I go to second number 5, I grab c, but I grab number 1, and put in my argument x. Okay, the next one I don't want to change. The next one I don't want to change much, so I just brought them down. Use the left arrow and put the minus sign in. And that saves a little typing time. Okay, since I've traveled this road before, I found the best window is still minus 4 to 4. But for the other, minus 15 to 15 instead of 1 to 15, minus 1 to 15. And that was just after playing with it and trying to get a good curve. Are you ready? Okay, the graph. The first one you will see is the graph of cinch. Notice how it's different. Comes out of the third quadrant and then heads up. Okay, the next one you see is asymptote for the right-hand branch. That's y equals e to the x over 2. Then coming out of the third quadrant, you ought to see another curve. There it is, which serves as an asymptote for the left-hand branch. And they're hardly distinguishable, but you can see them. Trying to remember. There was a way. No. To highlight it. Pick number 6, I believe.
Like to change the symbol.
Change the style.
Yeah, there you go.
And I think I'll make it thick. I'll do the same thing for that one. So it becomes a little more apparent. Then I'll try it again. So here comes the graph of cinch one more time, just ordinary. But I think you'll be able to see the asymptote a little better if I make it draw it thick. So here comes the first one, and can you see it? Yeah, that's a little better. And then here comes the other one. You can see it now coming out of the third quadrant and veering off. So why are these things called hyperbolic functions? Because they have asymptotes, just like hyperbolas do. What's the difference? Asymptotes of hyperbolas are lines. These are curves. So if you didn't ever realize that before, asymptotes don't have to be lines. They can be curves. It's how they're acting that determines it. And what is asymptotic behavior? The further you go, the closer and closer the curve goes to whatever the asymptote is. And here's two curves converging in on each other instead of a curve converging in on a line. Okay?
So is that why, like, right on the base of the,
It was the cosine, the one you drew first. Right at the base of the vertex, let's call it, the gap was bigger
Yeah.
because it's going to start shrinking.
Right. So your biggest gap on the right-hand branch, you're right, is right by the vertex. They're half a unit away. And then that gap keeps narrowing down. Right. Okay, if you want a little record of the one we just did here, I told you what the asymptotes were, but I did not draw the results. We looked at them on the calculator. And this is what we got. The cinch curve kind of went like this. This asymptote came along like this, and that was y equals 1/2 e to the x. The other asymptote came like this and went that way, and that was y equals minus e to the minus x over 2. This is y equals e to the x over 2. One last final observation before we leave those graphs, and you can explore tangent the other ones if you like and see what they look like. But I want to have them both together on the same screen. Did you notice this asymptote? It's under the curve, see? And that's the other thing that's worth noting. Whereas this asymptote, yeah, it's the same one, but the curve is under the asymptote. So the question often is asked, is this exactly the same curve as here? No. It's moving in exactly the same direction, but it's below the asymptote instead of above it. One's above, one's below. That's the difference between them. So if I graphed cosh and cinch only in the first quadrant together, I should see two separate curves, but staying totally parallel to each other, parallel curves. Okay?
Because they're following the same asymptote.
Yes. And the asymptote is exactly midway between them all the way.
Good stuff. Well, parallel with respect to that asymptote then.
Parallel to each other. They keep going and never intersect, but usually we limit the word parallel to lines, but you can talk about parallel curves too. Okay, the next item is D, and that is applications. And for that, we're going to go to the computer and see what it tells us. But one of them I want to mention, which is also on there, is you have a couple of telephone poles and you hang a wire between them, and that's kind of the origin of the name catenary. Sometimes if you're trying to impress your friend, you might be going down the road and say, look at those beautiful parabolas demonstrated in the hanging wires. If they say that to you, then you say to your friend, you are showing your ignorance. These are not parabolas, these are what? Catenaries.
Wow.
In other words, if you wanted to graph these using a function, you have to use a hyperbolic cosine function to do it. Now, what does that matter? Well, you see, one of the things that might be pertinent is how long is this wire between, right? So you adjust them to a certain tension that's predetermined. Then you like to know, well, how much wire do I have to bring? How much wire is there in between? It's not straight across. Well, in calculus 2, there's a formula using integrals for calculating length of curves. See, distance formula is great if you have straight lines. But there is a formula in Calc 2 for calculating lengths of curves like this. All you have to know is the function that represents it. So if you know this is a catenary and represented by a hyperbolic cosine function, it's not hard to get perfectly, exactly the length of that curve, which will vary depending on the tension, but the coefficients in the equation are adjusted for the tension. Okay, that's one. It measures hanging wires between two poles.
Very nice.
Random question. Do you think tension would probably be standard?
Probably not. It probably has something to do with the poles and what they're hanging them from, what they'll take. I don't know. You look it up for us and let us know, okay? All right, let's see what we got here. Okay, the very first one, as you can see, is one application of hyperbolic functions. It's for making functions to represent hanging cables of any sort. If you look at this one here, it gives you a little better idea. They've got a little drawing of a wire hanging between two towers, and they've got an example of what kind of a function it takes to do this. And you notice those variables are A and B. You put different numbers in and you get different tensions. One has to do with the height off the ground and so on. The derivative, of course, is also given there, and there's the length of curve calculation right from Calc 2. Notice the use of integrals, and they use the formulas, and you can actually do a calculation. Okay, one of my favorites is right here. Have you ever seen that before? Have you ever been to the Gateway Arch in St. Louis? That is an inverted catenary. I find it interesting when I visited there. Been there more than once. You kind of stand around and listen to people talking, and those that think they're in the know talk about that beautiful inverted parabola. I kind of go, oh, it's a catenary. Kind of look, what's the matter with that guy? And they pull their little children closer to them, sort of thing.
Why would they put this in a pre-calculus book?
But notice the functions that are used to build that thing have to do with cosh again. okay, and they give you some basics with that. But what I want you to understand is there's something about why the architect chose that particular shape. And if you ever get to a museum, a science museum, go to the children's section. But make sure you bring a little kid with you, because if you go by yourself, you get into all kinds of, the guard asks you what you're doing there and that sort of thing. But the reason I go there is to see if they've got a demonstration of the catenary. And what you have is blocks that you can stack on a board that's flat, okay? And they stack perfectly in the shape of a catenary. That's the way they're shaped. You stack the blocks and they all lay on that board that's horizontal, okay? And after you lay it on there, and they're not Legos, they're not snapped into place, they're just lying against each other. Okay, then you take this board and you rotate it, and gravity holds it together against the board until it becomes vertical, okay? And when it becomes vertical, that arch does not collapse. You lower the board down and it stays right there.
It's a property of that.
Have you ever seen that?
So archways on like the outfields or
I don't know about those buildings. They're not necessarily that way, but the reason the architect chose that one is the forces inside that thing are in such harmony that you can build it out of blocks and it'll support itself. Now think if you made that out of stainless steel and then welded it all together, what a strong structure you would have. And so he based it upon this mathematics and the properties of a catenary. Yes?
Exact same thing, except for an inverted, what was it called? Parabola. Wouldn't work? Not even close?
It would probably collapse. I think so.
Now, is that sort of kind of like an egg, you know? Egg gets stronger at the
At the end points.
end.
Yeah.
that
The
can-
shape of the egg, I don't know if it's an ellipsoid naturally or one of these, but that might have something to do with it.
It is a circular shape like that.
I don't know. But this is a property of it, so that if you build it that way, think of what a strong structure you have. And if you have some time, I don't have time to do it in here, but you should look up properties of the catenary and look up the St. Louis Arch, and especially the architect that did it and that sort of thing. It's very interesting, the mathematics involved.
Strong from the top, right? You're pushing down on it?
Gravitation.
Well, it holds together even without the welds in place, but they basically built it out of blocks like that, stainless steel that were hollow inside, so that they could have a little tram that goes up to the top and have a lookout up there, and they welded the stainless steel together. But as they put the thing could stand by itself without the welds and the anchoring. But I think it'll stand, if I remember correctly, winds up to 120 miles an hour, and it sways. I was up there when the winds were about 50, and the thing sways. It's a little disconcerting, but I said to people, don't worry, it's a catenary. It'll take it.
They Charlie, they said, okay.
And again, that's the whole.
Again, they pull their little kids closer and talk about that. Okay, the other one that's kind of interesting is it takes hyperbolic functions to model the path called a tractrix. And when you have a semi-truck, turning like that, and you want to follow the path of the rear wheels, the path it's following has to be modeled by a hyperbolic function. That's the only one that matches. Same way if you pull a boat towards a dock. In other words, not straight towards you, but it's off on an angle and you're pulling it in on an angle, it follows that same path. And you can go on and on. You could spend an hour real easily just looking at different ways this, one of my favorites, which I hope to show you on Monday, because I lost that one. And I don't want to take time to bring it up right now, but it's riding a bicycle with square wheels and being perfectly smooth. One of my goals, if I ever can find the time, will be to build a little train that goes around the living room. And it has square wheels, but it runs perfectly smoothly.
Oh, well, yeah. And slots, I guess.
And it takes a hyperbolic function to construct the track so it'll do it. But there's a nice little animation on the computer I hope to show you on Monday. Okay, I have to do a little bit more with those so that you can work on those hyperbolic functions. Most of the stuff is now in. Now it's just a matter of what our problem's like. So this is E. Working with hyperbolic functions. Number one is evaluating. And the first example here is I want to find the cosh of natural log of 3. Yes, you could type it in your calculator and it would probably do it just fine. But I want to go through the steps doing it by hand so you can see why the answer turns out the way it does. You do have to remember that the cosh of x in general was what? E to the x plus
To the minus x.
Okay, got to remember this. Okay, if I fill that in for cosh of natural log of 3, I will get e to the natural log of 3 plus e to the negative natural log and divide by 2, right? Right, but I want to see what that really turns out to be. So going down here, do you remember what e to the natural log of 3 is? That's one of the properties of logs. 3. Now this next one I want to be a little bit careful before I just say what it is. This is like minus 1 times that, so that'd be e to the natural log of 3 to the negative 1 power, being careful. Because the minus 1 can go inside as an exponent. So it's really 3 plus e to the natural log of 1/3. Okay, but where is that going? 3 plus what?
3 plus 1/3.
1/3. And of course, the standard way to handle that might be multiply by 3 over 3, or whatever you do. It doesn't matter to me as long as you can do it. But you get 9 plus 1 over 6, which is 10, 6, which is 5/3 answer. So what is the cosh of the natural log of 3? It's 5/3. Okay, number 2. Just like in trig, you get a chance to do proving identities. For example, by the way, those properties we gave you of hyperbolics, they're proven in a similar fashion to this one. This is not one that's worth remembering. But I claim that if you take the cosh of x, subtract the sinh of x,
Can you move it
the
up?
answer would just be e to the minus x. So cosh minus sinh is just e to the minus x. And you're supposed to prove it. Now, just like in trig class, we demand that you use good form, which is start at one side, keep changing it till you hit the other side. Which side do you start on? It doesn't matter. I usually start on the side that looks the most complicated. You're only allowed, you don't have to give reasons, but you do have to do just one move per step. So if somebody said, what gives you the right to do that? You could say, well, I just use this. So it's not see how fast you can get there. I know the answer. I just want to see the steps for getting there. So what can I do with cosh? Right, I can write it as e to the x plus e to the minus x over 2. What can I do with sinh? Write it as e to the x minus e to the minus x over 2. If somebody said, I have no idea what you're doing, you could say, I'm using the definitions. This is by definition of the hyperbolic. You don't have to say that, but if you get backed into a corner, you should be able to come up with a reason. Just one. Okay, the rest of it is just doing algebra. If you have two fractions with a common denominator, how do you put them together? Add the numerators. Be careful though, this sign changes. And if somebody said, I have no idea what you just did to get from here to there, I would say, adding of fractions with a common denominator, right? I can give a reason that they should be able to relate to. Okay, what can I do next?
And subtract. And then add the other one.
So I get 2e to the minus x over 2, and if somebody said, I have no idea what you just did to go from here to here, I would say I combine like terms, right? And then finally, what is this equal to?
E to the negative x.
And if somebody said, I have no idea what you did to get there, I'd say I divided the common factor. So you have to be able to come up with a reason if you have to. That's what I mean. This equals this, which equals this, which equals this, which equals that. Now if you stop there, I won't say anything, but technically there's supposed to be a last step. Therefore, the first thing you started with has to equal the last thing you ended up with. And that's called transitive property. If a first thing equals a second, and a second equals a third, and a third equals a fourth, and a fourth equals a fifth, then transitive property says first has to equal the fifth. And if you want to put a little flourish on it, you can do that.
What is that?
That which was to be shown. Quid est demonstrato. That which was to be shown. If you're proud of your proof, you write that at the end. Okay? Well, I messed up.
You messed up.
Yeah, I'm not done. I should have cut off the related rate problems sooner. Okay, how far can you get? That means that I really can't justify giving you the test next week, Thursday, because you're going to be doing a few more hyperbolics between Monday and Thursday. And I like the sections to be done the day before, or the session before the test. So I'll tell you how far I would like you to go with hyperbolics. It's kind of giving you a break though, because if you need to do quite a bit of work on your project yet, there isn't going to be much to compete with it. I'm in section 311. How far should you be able to get? Through 17. So as you can see, we went really far. So you can do 3, 4, 9, 13, 17. Sorry. To be continued on Monday. Don't forget your projects are due too. Any questions? Holland, you were pretty quiet today. Are you all right?
Yep.
What do we call the graph of a hyperbolic cosine? Holland? I was really communicating, I can see that.
Yeah, I have a question for you.
It's the cat that ate the canary, come on. Pardon? Think that would work? Because it's Holland?
Okay, Kelly and I had a question. We're both signed up for, Monday and Thursday night. It just says staff. We were wondering if that was good.
They won't tell me.
They won't tell you?
Now that I'm not full-time anymore, they